Great, welcome to GIS for Civil and Environmental Engineering Systems. All right, in this course, we will be covering a range of topics. I will actually be starting with the GIS crash course, we'll call it, kind of a boot camp style. We'll be spending about 5 weeks focusing on learning the fundamentals of what GIS data is, and we'll talk about that in a second. And the software that is pretty much the dominant software for GIS, which is called ArcGIS Pro. Then we will transition into GPS surveying. So this is essentially a total station. It's not as accurate. However, it's a lot more versatile. And for basic topographic surveying, like getting topography for a site plan or something like that, it works great. Once you kind of get the technology and workflow going, it's pretty easy to use. And we'll talk about, there's kind of different versions and systems out there. It's really great equipment, and I'm excited that we have it and that we can learn it. We'll get back into GIS and do some more advanced applications, more specific to civil engineering. So a lot of this will deal with dealing with topographic surfaces, collecting data, creating surfaces yourself, comparing them. And then we will finish with photogrammetry, which is creating digital elevation models or topography using photographs. So it's super cool. 3D models essentially with photographs. And so you'll do it with your phone cameras or whatever camera you have available. And then we'll also do it with drone imagery. And we'll create a surface based on that. So it's really fun. There'll be a class project that we'll talk about a little bit later in the course. Here's how the course is broken down. We'll be doing these tutorials, these ArcGIS tutorials. I'll be kind of grading them as a plus, check, or minus, basically. And we'll get into what I expect in these tutorials, but you're basically going along and following kind of these step-by-step instructions in the course textbook. And then you'll be documenting kind of some of the major steps along the way, answering some questions, and then writing a summary of what you did. If you took statistics, I think everyone's taking statistics with me, a little bit similar to that. Not as involved, we're not doing R, but documenting what you did and then writing a little bit about it. We'll have some reading quizzes. I'm going to try to do them weekly. It's probably not always going to happen. And those will be just be something you'll do online on your own time based on the reading in the books that we'll be reading. Then we'll have homeworks and labs kind of sprinkled throughout. The beginning kind of 5 weeks of class will be focused on the tutorials and getting through and doing some of the book work to get started and spun up on GIS. There'll be probably 1 homework sprinkled in there, maybe 2. And then, homeworks and labs, I kind of distinguish them. There's probably only going to be like 2 homework assignments that are like a little more involved in this class. And a lot of it will be doing a lab where we learn a skill, we learn kind of a new type of data, and then we work with that data and do some analysis with it. So those are kind of lumped together. Mostly we'll be focusing on this on the latter half of the course. So tutorials kind of up front and homeworks and labs towards the end. And then we'll pick up this class projects. We'll talk about this. You can work in pairs. I think we have an even number, we'll see. To do kind of a bigger GIS type analysis with engineering applications. I have a bunch of examples of types of projects you can do, and you can do those, or you can come up with your own. So as we go through this course, if there's kind of a cool GIS data set out there and type of analysis that you're interested in doing, I'd love to work with you to make that happen. So we had a group, the first time I taught this class, do a transportation analysis and connectivity analysis to look at if we were to have bike trails in all the canals, how that would change the network of bike paths. And so there's a network analysis you can do. Yeah, and there's a lot of hydrology applications. So as you take hydrology with me and you're kind of thinking about and learning the tools and skills there, if there's something that excites you about that, we could do a hydrology related project. As for class expectations, it's important to be in class. If you can't, let me know. I will write my cell phone number up there if you need to kind of text me. Actually, to be honest, I'm going to be taping all of these anyway, so they'll be posted. So if you need to miss class, no big deal, but the lecture will be posted. We won't have a ton of lecture time. Most classes will be doing an introduction to concepts, maybe spend 15, 20 minutes doing that. And the rest of the time we'll be working together and problem solving and troubleshooting to do the different examples and applications. Please keep your cell phones silent and off the desks. I'll be communicating and posting everything through Canvas. So please subscribe to announcements on Canvas. And we'll look at like the first week of Canvas, but everything you need for each week is going to be there. So week 1, what readings do we need to do? What assignments are posted? If there's supplemental materials out there, maybe I'll put a video on there or an article that's pertinent. My office hours is posted on Canvas, and it'll be outside of my office itself. I encourage you to work together. Often you can get stuck on something. ArcGIS, just like AutoCAD or Civil 3D or whatever, has its own set of file management, data management. This basic file that we work with in Arc is a shape file or a raster, and they have all these different files associated with them. So it can get really confusing, and it's really easy to get kind of hung up on something when you're just learning it. So if you can find a buddy to work together and do these tutorials with or homework assignments with, that's great. And then software, we'll mostly be working with ArcGIS, and I'll talk about it in a minute in a little more detail, but that is available in 305 on the computers here. It's available in the informal computer lab downstairs and the second floor, as well as the formal computer lab. I always forget the numbers, but I think it's 217 and 218 or something like that. And then you also will be able to download and run the software on your own computers. It needs a decent, chip in there, right? Processor. So you can look at the software requirements, but you can get a free license through the university to download it and run it on your own personal computer. Here's our text, Mastering ArcGIS Pro. This is required for the class. And this is where the tutorials and readings will come out of. We'll also be reading from different sources. This is an online textbook about GPS. That when we get to that section, and then UNAVCO, which is a research nonprofit based out of Boulder, and they have a lot of great materials on photogrammetry and some of the surveying techniques that we'll be working on. Any thoughts or questions so far? All right, let's get into what is GIS. It's Geographic Information System. I should have written that out, but Geographic Information System. And so it's kind of a funny acronym. We say GIS Data, Geographic Information System Data. We work in GIS. Do you know GIS? Do you do GIS? I have some GIS work. It's kind of thrown around as a noun. It is a noun, but it's got some funny uses. But what it basically is it's not that hard. It's a map in a database. And so the system means it's a lot of things. It's kind of an umbrella. And within that map and database, so the database is a table, and a table could have information on a number of things, but that table is connected with spatial data. So geographic means spatial, right? So we could have vector data, and that's just points, lines, polygons. Vector just means it's a string of coordinates. And so those coordinates are connected, either they're points or they could be connected to create these shapes. We could have raster data, and raster is simply like an image. So if you think of a bitmap image, right? You zoom into it, you see the pixels. Each pixel has a value. A color raster a color picture has 3 layers to it. And so there's a red, green, and blue layer, right? So rasters can have multiple layers to them, and each cell has a coordinate for the center point and a value. It could be a color value, it could be a data value, it could be an elevation value. We'll be dealing a lot with elevation rasters where each grid cell has a coordinate and then a Z value. TINs are triangular irregular networks. So it's kind of like bringing a vector and a raster together. It's not a grid. So you can have kind of random points, but they're all connected as triangles and they create a surface. So it's another way to represent topography or elevation. And then tables. So tables are typically going to be connected to vectors or rasters. You can imagine a series of points, just very simply of addresses, or precipitation gauges, or bridges, or something like that. And each point has an X and a Y value, maybe has a Z value. And then it's connected to a table which has information that we're interested in. Maybe the age of the bridge, maybe the last time it's been inspected. For civil engineering, we have GIS data and databases for our road networks, right? Each city is going to have it of all their utilities and that sort of thing. It's a great way to keep track of where things are and how they're doing. This image, before I go, is a raster. So it's a gridded data set, and each little pixel has a value. And it's showing you the Ogallala Aquifer, which is in the high plains. So here's Lamar, Colorado, in the eastern plains. And the aquifer shows you how, this shows you the projected usable lifetime of the aquifer. So green is by 2100, and then orange, I guess, is 2009. So there's a lot of areas in the aquifer that are kind of drying up and going down. And then there's some areas that are doing a little bit better. So this is raster data. Each point has a X and Y value. And then the cell itself has a, in this case, a categorical value. Here's another raster. This is the burn probability for Colorado. Honestly, I think this map is garbage because if you notice, this is Larimer County, and all this blue is exactly where the Cameron Peak fire happened. And all of this, here's Grand County right here. This is where the East Troublesome fire happened last year. So there's a lot of data out there. Some of it's good and some of it's not so good. This is in a case where you bring a lot of different data sets together and you put some probabilities and weights and you come up with this index, and maybe it's valuable and maybe it's not. In this case, I think this is a pretty not valuable data set. Here's another type of data. These are USGS gauges for the state of Colorado. It's just point data, right? X and Y values. And then it's streaming so that this map is linked to all the stream gauges on their server. And the stream gauges are talking to the satellites and telling the main server that USGS has how much flow in CFS is in the stream at a particular moment. And so what they've done is color coded it based on percentile. So if you look at, say this is August 6, 2019. So if we look at all the August 6, 2019s in the record of the stream gauge, I think you need at least 10 years of record. And then we say, what percentile are we in? Green is kind of in the middle, right? Between 25 and 75% of observations. Dark red is below 10% and dark blue is above 90%. So back in August of 2019, streams are doing pretty well overall. And that's just kind of a good indication of the overall flow in a particular moment of time. So that's kind of another cool thing. You can have static databases. It's just a table that you upload on a database, or you could have it linked to live data. In this case, this data set every day is being updated. through this web map. So we've already talked about this, but here's another more detailed look at the difference between raster and vector data. So this cartoon represents the surface, or just something we want to represent digitally. And we could go the vector route, and we could draw lines where streams are, and each vertex in this line has a coordinate, and then they're connected to each other as well. So there's information in here, not only of what's connected, but also network information. So what flows into what. We could also represent things as points, locations of, say, cities or towns. And we could represent things as polygons. So these are just vertices that are connected and enclose a certain area. Rasters can do a similar thing. It's just different kinds. It's a different way of representing data. So streams can be represented as grid cells like this. And actually, we'll go through an exercise which takes a topographic model, a digital elevation model, and you generate a stream network in the raster out of that. We can have points in a raster, so no data values and then data values. And we can also represent areas in a raster. And in ArcGIS, you can convert between one and the other. So here's another look. If we have the real world, we could have an elevation model of that real world. Maybe that's collected from all the old USGS maps that they digitized, or LiDAR data, which is flown in an airplane. It's an infrared laser that scans the ground and we get elevation. We can have a raster that represents land types. And if you do engineering hydrology later on in your career, you'll be going to look for data sets like this because you want to know how much pavement and trees and neighborhoods are in the watershed draining to a certain area. So these are two raster data sets. We could have parcel data sets. So where are all the property boundaries in a city? Where are the homes? We can have a road network. And then political boundaries. These are all vectors. These are polygons, lines, and polygons. This is what vector data looks like. It's just coordinates. Sometimes we can have added information. So that could be a directional line, meaning it starts here and it ends here. So that would be a route. And we can also have networks where we have multiple lines coming together and they're connected by nodes. And a lot of transportation engineers will do network analysis on road networks. So we kind of talked about points, lines, polygons, rasters. Within the other part of the GIS information is attributes. So say we have a point shape file. We know that this is a point shape file of restaurants. And then the attributes, which is a table connected to this, we have information like address or type of food. For roads, maybe that's the length of the road and the speed limit. For countries, we could have information on the population, GDP, et cetera. There are two types of data that we have for rasters. So remember, raster is a gridded data set, just like an image. We can have continuous data. And if you remember from statistics, what does continuous data mean versus categorical? Yeah, there's no, so continuous simply means it has a decimal point, right? Categorical, sorry, I should have said discrete. For statistics, we call it discrete data. And so we have discrete PDFs, right? It can only be a 1, a 0, 1, 2, 3, 4, right? So those are integers. And that's what categorical data is, it's discrete. We typically say categorical because the numbers really refer to some description. So this raster right here might have 1, 2, 3, 4, 5, 6, 7, 8 values in it. So if I go click on this cell, it's going to give me 1, 2, 3, 4, 5. It's going to give me the number 5. And then I have a table that tells me 5 means forest, right? We don't want a 5.7 because that's going to be somewhere between forest and barren, and that doesn't make any sense for this data set. So categorical data has discrete numbers. Continuous data can be, 1507.2345. And a good example of that is elevation data set. So this is a digital elevation model with continuous data. Here's some other examples. Aerial imagery, we'll use a lot of aerial imagery, which has been taken from an airplane or a drone and then georeferenced, so that it lines up in a coordinate system. Digital elevation models, land cover, precipitation. You can imagine a raster of precipitation, annual average precipitation, for example. A lot of information out there. Let's talk about mapping scale. And this is something that all these topics are in the first chapter of the book. So we're just going to introduce them, and then you can read about them in more detail in the book, and we'll work with them as well. Here is a very beautiful, I think, USGS map that they lovingly hand painted. Does anyone recognize where this might be? Yeah, the Colorado National Monument. And here's No Thoroughfare Canyon. And that was a beautiful map, so I wanted to share it. This map was made back in, 1962, it looks like. And they used pretty rudimentary but good techniques for generating these contours. And we'll talk about that a little bit later. But they used photogrammetry, so they had an airplane flying and they had 2 images taken, stereo images that created basically a 3-dimensional image when you put them together. And they had a good technique for identifying contours and elevation and drawing all these by hand. So the entire nation has been mapped using that technique back in the 40s, 50s, 60s, and 70s. Yeah.
I remember the store downtown, but they have like found stuff you can go buy.
The bird's nest or robin's nest.
Maybe, but they have all kinds of different stuff, and they have a collection of like glass pictures of
Yes.
from the planes, and they're really old, and they're of this area, so
That's cool. I'll have to go look at
I
that.
almost bought one just to,
It's kind of cool.
Yeah.
Put on the knick-knack shelf.
yeah, but it didn't mean a whole lot to me. I feel like it will after this class.
No, yeah, absolutely. I love that. And that, it was before TV, right? They had 3-dimensional images, and they had it was like postcards. They would take a stereo image of some national park or some events, and then you'd put it in a special viewer and bring it together, and you get a 3D image. So they would do it for, just interesting things to look at for people to buy. So this map has a scale associated with it. And I enlarged it right here. The scale is 1 to 24,000. So that means 1 inch on this map. You multiply that by 24,000 to get the real length on the map. Okay, so you guys are probably familiar with scale, and but the important thing is to know that there's a certain kind of, you can think of it as a resolution on a map. So if I were to want to know with certainty how wide the Colorado River is on this map, and I measured it, I can estimate how wide it is using that scale transformation, right? So how many inches is it here? And then I can do the 1 to 24,000, or I can use this actual scale bar here. But then what's the accuracy of that? Because there's an accuracy associated with drawing those lines and mapping at this scale. Here's a similar map. This is the Grand Valley and beyond at 1 to 250,000. So you can see the resolution is much smaller. I can still zoom in and find the Colorado River, but now it's kind of a line instead of a shape. So we'll kind of get into exactly what this means, but there's a way to estimate the spatial accuracy of something based on the mapping scale. And obviously, the larger the scale is, the less accurate something is. If you're going to draw a line from point A to point B, that's going to be plus or minus a larger interval than you would at a finer scale map. Here's another look at mapping scale, and this is the coast of New Jersey. In purple, we have the coast of New Jersey. If we were to look at basically a global map or national scale map of our country. So it's really rough, right? They're just kind of drawing the overall boundaries of the state. And you wouldn't want to make a map of New Jersey at this zoomed in scale with that data. So this is 1 to 25 million. Huge data set. Maybe you're going to make a map of the whole continent or the globe or something like that. And it doesn't matter how accurate you are with a coastline. The yellow is 1 to 5 million. And this might be a state map. We get the rough idea of the county boundary or something like that. The black is 1 to 50,000. This is more of a county scale map where we more accurately maps the coastline. Why do we not always want to include the finest scale in a mapping project or data analysis project? Yeah, it's just, you could think of it as too much data. If we had this 1 to 50,000 scale type of data set for the whole globe, that would be huge, right? Think of all the coastlines, and we're measuring it to a really high degree of precision. So we don't always need that information. And so understanding kind of the coarseness or resolution of our data relative to the mapping effort we're interested in is going to be important. So we don't always need the best data set or the most high resolution data set. So let's zoom in to the 1 to 24,000 and 1 to 250,000. So this is the same area. So think about how precise the data would be. Say I were to digitize the Colorado River just by, kind of creating a polygon and clicking along here. And how accurate would that be if I were to do the same on this map in terms of where exactly the river is? So here's just an example of that. This is a pipeline network for the country. And a pipeline digitized from a 1 to 100,000 scale map would have an XYZ accuracy of 170 feet, which is essentially based on the thickness of the line. So if I'm drawing a line at this scale, it's going to have a certain thickness associated with that. And if you think about what that thickness represents on the ground, that's going to be about 170 feet based on someone's ability to digitize something at that scale. So the finer scale you get, the more accuracy you get as well. So mapping scale is related to the resolution of your data and how precise that is. And then source scale, which is a little bit different, is when you take a map, like a paper map, and you digitize it, what's the resolution of that original map that data came from? So I'll say we're to digitize this river again, I'll have a digital data product, but it's only as good as the scale of the original document that I digitized from. All right. There's a lot of engineering applications in ArcGIS. Has anyone dealt with this in their own engineering lives and worked with GIS data or collected GIS data?
Those 400 projects, the GIS guide, pull, we get working these things for our action points.
Was he using a GPS survey, do you think? Like did it have kind of like a round antenna on the top or a prism? Yeah. Great.
And then tablet. And then here to also use that to make maps for that.
Nice. Yeah. So, and we'll actually get to do all that later in the semester. So he was collecting topographic data with the GPS.
Yeah.
Nice. Any other experience with GIS? How about for the route? Yeah, Edgar. Nice. What were you doing? Mhm. Oh, QGIS is the free version that's out there, and it's nice. So you had a crash course using crash data. That was a joke. So you had like a.
I like the point you mentioned.
Nice. That's great. Justin, were you gonna say something?
I just think they like the guys on like on projects are constantly taking shots of like the pipe and putting in. As like an inspector, we don't actually have that, so we just go on to theirs.
Mhm.
So we make sure that they like a hundred of what the plan, what the design was.
So that's your tolerance is like 100th of a foot?
Yeah.
Okay.
So yeah, we usually just make sure it's there and then it's good. And if they find like utility that wasn't out before, they'll shoot that too. Just like,
Yeah.
but yeah, it's I don't actually do it. But
Mhm.
see them doing it all the time.
So when you're out there on a construction site, you got the drawings, we have to make sure it's in the right place on the planet. Yeah, and you'll see they'll set their base station up, which we'll do here is we have that same equipment. They set it up in that tree area. They've got a control point. And so everything's based off of that one control point. They probably have more around the site, but yeah.
It's like 4 or 5.
Okay. Yeah.
Another big one at CDOT is like, I don't know if you ever heard of survey 1, 2, 3.
Mhm.
It's like, but like there's an ADA ramp that's being built, you have to go to that ADA spot and it's on your phone, it just takes you coordinates. And then
Nice.
you fill all the data that corresponds to that.
Mhm.
It's kind of weird, it's just so much data.
Yeah.
Like this.
Yeah, it's a lot of data and there's these systems now where they'll have applications, you'll be out in the field and there's some form that you're filling out and that goes back to a server and it's cool stuff. Yeah, so in that case, you're probably collecting a points and then putting some attributes on that point for
Then
the.
you go back later or on the map and it shows all.
Mhm. Nice.
Yeah, that's like I would do the forwarding these things from the guy. I would put them into so maps.
Okay. So you're bringing in the XYZ data. Yeah. Nice.
Oh, yeah.
Great. Well, northing, easting, elevation, XYZ. Yeah, we'll learn all those terms too. So here I just have some other engineering applications, drainage and hydrologic analysis. That's going to be a big one. We'll actually be doing this in hydrology. So you can use a digital elevation model, which is represented by this hill shade image to delineate watershed boundaries and stream networks. This is, I don't actually know what this is. This is identifying culverts. It looks like that block fish passage. And so they are going along a road and mapping what culverts are and figuring out where they need to upgrade culverts so that fish can migrate upstream. A lot of using GIS and, CAD and topography and drawing, that's its own whole thing, right? GIS isn't CAD. CAD has a certain level of precision that's important for the site scale. So we're typically talking about kind of mapping applications, and mapping is kind of more of a planning tool you could imagine, but it all communicates with each other. And actually CAD and GIS can communicate with each other. You can import and export stuff. So I would consider GIS a kind of cousin of CAD with some different applications. The precision is typically not as high as CAD has, or at least the data sets that we're dealing with, but we will in this class learn how to use GPS surveying equipment to get XYZ points to then import and make surfaces. So it's good that you already have some experience with that. Here's a pipeline. This is a water supply pipeline from the San Juan River in New Mexico. And a lot of GIS work happened to plan for its alignments, understanding what the slopes would be to get water from point A to point B. You can imagine how you'd have property boundaries on this and to figure out what kind of easements you would need and how many creek crossings you have. So a lot of at the planning level, you would use GIS, and then you would have CAD for the actual design and construction end of things. And similar to what Justin was talking about, managing infrastructure networks. Say we have a tablet and it has a GIS in it of the existing infrastructure network. Maybe it's utilities, maybe it's road networks, maybe it's ADA ramps like Justin was working on. And we could go around and collect data. What's the status of this? Is the condition okay? Is it where we think it is, et cetera. Here's a map that we'll deal with in hydrology that shows the 1% annual exceedance probability, 24-hour rainfall depth. And in Junction, that is somewhere just under around 2 inches of rain. We got 1.5 inches of rain over 48 hours. So not quite the 100-year rain depth, but probably pretty close or pretty exceptional last week. Here's a map that I made showing stream gauges. So here's all the stream gauges in the state. Not all of them are active. Some of these are historic. And what I did is I took the stream gauge data that I had. So this is actual flow data from all the stream gauges. And then I said, give me the peak discharge, the highest flood that's ever happened at this gauge, and then divide that by the average flood at the gauge. And so what this is showing is where you have more extreme and less extreme floods. So the bigger purple dots are anywhere from 4 to 30 times. The most extreme flood is 4 to 30 times the average flood at that gauge. So you can imagine where it's blue, the most extreme flood isn't that far away from the average flood. Where it's purple, the most extreme flood is much farther away from the average flood. So this was a mapping exercise to look at flood intensity across the state. And once I did that statistical analysis, really it's just dividing, then I attached the XYZ data for each of the stream gauges and then mapped it. Yeah. Mm-hmm. Yeah. Why would you have a really extreme flood gauge or stream next to one that's not so extreme? Yeah, and I didn't drill into that level of specificity. It's just more kind of looking at where do we see more purple dots and where do we see more blue dots. And so in general, you could say, well, there's more extreme flooding on the Front Range and in the Arkansas Basin, but we do have extreme flooding on some of these smaller tributaries in the mountains where you can have, basically debris flows like what happened in Glenwood Canyon. But yeah, it could be that, this stream is a tiny gauge that doesn't have a very long record and maybe a really big rain event hasn't hit it yet. That would be my first guess. All right. Let's see. Let's take a stretch break.
Oh, I think that was so good.
So let's take a minute to talk about the software we'll be using. So for GIS, we'll be using ArcGIS Pro. And here's just a screenshot of it. We'll get into it next class. And you can make it look black and look cool. We'll be doing GPS topographic surveying. I won't get into the details right now, but it has satellites and stuff. There's a base station, there's a rover. The base station is set up over control points that we know to a high degree of precision. We also have what's a virtual reference network in Mesa County, and this also exists on the Front Range. And in this case, you only need a rover and a Wi-Fi or data connection, so LTE connection, and 4G, 5G. And with that, basically there's a bunch of reference stations that are permanent GPS antennas around. They talk to a server, and the server is connected to the cellular network. And then with your rover, you can go around and you have basically free reign to do the same kind of GPS surveying you would do, except without a base station. So this is really nimble. You don't have to deal with a base station, which is a lot of work. And you can kind of just open it up and start collecting data on the fly. We'll look at it when we get to that, but they are all, there's a network that extends, I think, from Craig all the way down to Durango. So it covers most of the western slope. The only challenge is that you have to have cell phone coverage. And obviously there's a lot of areas in the western slope that you don't have cell phone coverage on. So it's one drawback. This is the setup. You've no doubt seen this either on construction sites or use this yourself in some cases for some of you. Here's our base station, and here is our rover. It's the same antenna, and they talk to each other, and they also listen to the satellites. And then there's a Bluetooth connection with the data logger. We'll be using Trimble Business Center. This is software is available in the computer lab. I'll make sure it's available in the informal computer lab as well. And it's on the computers in 305. This is where we import our data from GPS. We'll do some corrections to it, and then we'll export it as a shape file, or you could export it to a CAD file. Here's a quick look at photogrammetry, and this is the last topic we'll do at the end of the semester. Old school photogrammetry dealt with stereo images taken from an airplane. And they had a whole process for identifying points and elevations associated with those points. They called them fiducial locations. And they had, using this manual, which is pretty old school, we had, I bet you the American Society of Photogrammetry is no longer active, but who knows. They had this whole process for basically drawing and connecting contours. So all these contours were drawn by hands, but using this, I don't have a picture of it, but it was this basically this top-down looking image. And so they would basically be like looking at this image and then kind of drawing over the image three-dimensionally, these things. So really cool, not 100% accurate, obviously, but that's how we got our topographic maps. So that was old school. Here's new school. We've got drones with cameras on them. And these drones will fly and take thousands of pictures with really high resolution of the ground. And there is an algorithm and software out that we'll be using. It's called Metashape from Agisoft. And it's actually a Russian company. It's kind of cool when you email them. You get a response from Olga, Kaslikova. It's pretty cool. I don't know. I don't talk to Russians ever, except when I email them. So what this software does is it based on crude GPS information, probably like plus or minus 3 to 10 meters, you get a location of where all these images are. So it knows on the drone where you took the picture and what the orientation of that picture is. So you put that information in, and then the algorithm essentially identifies pixels that match from all of those, and then is able to give you a three-dimensional XYZ values for all those pixels. So you get a point cloud based on photo imagery. It's not perfect. You can kind of see that there's some funkiness happening, and we'll learn how to deal with that. Here's the original images that someone took, and then here's a 3D model with those pictures oriented in space. So a lot of this is, making 3D models of buildings or objects, but we'll deal with making a 3D model of topography of the land. I think what we'll do is the pump track over there, unless someone else wants to do something else. Yeah, it's legit. It might be this kind of model. This is one of the bigger ones out there. Yeah. You ask if they're doing a flight and we can come out and watch them. That'd be cool. Mhm.
out there. They're just like, kind of, just like building.
That's cool.
Like, as it goes.
That's
It
cool.
took like 15 minutes.
Yeah.
Fully built, that's wild.
That's super cool. Well, our process will be a little more clunky, but what we'll do is you can ground truth it with ground control points. So we'll spray paint these circles, we'll survey them in with the GPS, and then we can go back in with the software and say, okay, this is this point and this is this point. We'll be able to scale and stretch the image that way. All right, so our first assignment is going to be on Google Earth. And here's just a project I have on Google Earth. This is some lines representing water area at different floods that came from a model on a river. And this is a river restoration project. And then these white dots are the well locations. So Google Earth is a GIS. It's a geographic information system. It's a lot easier to use. It's not as sophisticated. You can't do the kinds of analyses you can do in ArcGIS, but it's a really easy way to, you can export from GIS into Google Earth and make some quick maps to share, because a lot of people have Google Earth or access to Google Earth because it's free. So I use it a lot when I'm working on projects, and we can kind of share data points and make quick maps and that kind of thing. So your first assignment is to do this Google Earth tutorial that I've posted on Canvas. You'll download Google Earth Pro for desktop. It works on Mac and PC. So you'll need to do that on a personal computer because it's not on these lab computers. If you don't have access to a personal computer, let me know and we'll get you hooked up. What you'll do is create a path, which is basically just a polyline or a line. And you can click and drag and trace a path. And this is just whatever path you want. If this is your favorite hike, this could be the walk you take around your neighborhood, when you walk your dog, whatever that is. So I've got a path that I traced up to Liberty Cap. It's not my favorite hike, but it's a nice hike to do. Really gets your thighs working. And what you'll do is then you'll create a path, you'll create points at the beginning and the ending, whatever that location is. So these will be two things. You'll create a line and 2 points. And then you'll look at the elevation profile. And I give you all the instructions for how to get this information out. But it's just kind of clicking on stuff in Google Earth. So you'll kind of print all this out and you'll tell me what the elevation change is. Google Earth actually has a digital elevation model for the whole country embedded in it. So that's where this came from. It's really coarse, it's rough, but at the same time, it's something, you know, and it can get you the big elevation changes. You don't want to use it for engineering though. And then you'll share that with a peer and you guys can check each other's work out. So that when I mean share is you'll email it to someone and say, here's my, it's called a KMZ file. And so they'll open it and look at it and bring it into Google Earth and say, cool. So the point is sharing data and uploading data. And then the other thing we'll do is by next class, I want you all to, if you plan to download this and use it on a personal computer, to go ahead and do that. Again, it only works on PCs. And I'll share some links of how to do that. We'll also create CMU accounts. And so I'll need everyone's CMU email addresses. I'll email you if I don't have them. And we're going to send this out to the librarian who manages ArcGIS licenses at CMU. So what you'll do is you'll have an account. It'll look like this. So first initial, last name, whatever your CMU email is, _CMU_GIS, you'll create a password. And this is what you'll use to sign into the software, either on your computer or in the labs. So I have a tutorial posted on Canvas. You'll get an email from Laureen Cantwell once you have your credentials. She needs to set this up first. And once you get that, once you get those credentials, you'll take some steps to sign on and get your account activated and stuff like that. But I have information on Canvas I'll show you. And then finally, after that Google Earth assignments, I have this posted now, it's due next week, but I just want to let you know that we'll do the first chapter in this textbook. So you'll do a tutorial document, and I'll post an example of what this looks like. But you'll kind of go through these steps. First there's some reading, then you'll go through the actual steps of opening ArcGIS Pro and doing some stuff. Take screenshots of kind of important steps, not every step, but maybe the first step is to open a data set and look at it and mess around with it. And then at the end, you'll take a screenshot of what that is. All right. So maybe there's like 3 to 4 things that you do in a tutorial, and just take a screenshot at the end of each one of those major things. Include captions. So this is a screenshot of this data set that I did this thing to, right? So one or two sentence kind of caption. And then there'll be some prompts and questions along the way. And so I've identified which ones to answer. You don't have to answer all of them. And then provide a summary paragraph at the end. Here's your rubric for tutorial grading, and I'll make sure this is on Canvas to look at. So full, partial, or no credit. And then the last thing is there is an online portion to the book. You can get the book online, you can get a PDF of it, you can get a hard copy of it. There's a website, and I have this posted in this this presentation. It's also posted on Canvas, where you'll go and you can access as a student the data sets for the tutorial. I've also posted them on Canvas, as well as videos. And so the tutorials will have kind of step-by-step instructions with graphics. There's also a video where they walk along and do everything in the video. So if you feel like you would like to see that and have those videos to help, you can access them through this website. All right, any questions about that? No, let's take a look at when things are due, and I'll stop the recording. Okay.